Alright, welcome back everyone. Okay, we're talking about section 1.6 now. This is a library of parent functions is what it's called. And honestly, we've done a lot of this before, so basically what I'm going to do here for the video is just focus on the things we haven't done. What I mean by what we've done before is the library of parent functions are just all the generic functions we deal with, and then in future lessons we're going to talk about how to shift them and transform them, which admittedly we've done a lot, so we'll skip some of that at time, but basically getting to the point. This section talks about like parabolas and linear functions and absolute value functions, all those other ones that we spent some time graphing before. So basically what this video is going to focus on is the ones that we haven't done, which is going to be something called the greatest integer function, the reciprocal function, and then piecewise functions. Now we've done a little bit with piecewise functions, so hopefully that one won't be too much of a shock when we get to it, but here we go. Okay, the greatest integer function is defined using this special set of symbols. Kind of looks like a double set of brackets, and it's like the greatest. It's equal to the greatest integer less than or equal to whatever number you're talking about. Okay, now remember integers are your positive and negative whole numbers basically. Okay, so once we start talking about this, the greatest integer of 5.2 again is the one that's less than or equal to 5.2, and so that would simply be 5. When we start talking about 3.9, you might think, oh, well, this is just rounding. Well, the greatest integer of 3.9, again, is the greatest less than or equal to 3.9. So since we didn't quite make it to 4, this guy basically goes all the way down to 3. So this is kind of more of a truncation than rounding, per se. Okay, the greatest integer of 7, well, the greatest integer less than or equal to 7 is still 7. Okay, now hopefully you're feeling really cocky about this, and you think, oh, okay, well, negative 2.7, well, obviously that's negative 2. Sadly, you'd be wrong. Because, again, if you think about the greatest integer less than or equal to, well, if I think about a number line here, and if this is negative 3, this is negative 2, and let's just for giggles put negative 1 on here, negative 2.7 would be sitting about right there. Okay, and if I want to go less than or equal to negative 2.7, I'm actually getting to negative 3. Basically, more of the story is make sure you're being careful with the negatives as we got this. It's kind of like you're always taking it to the left. Everything you own, make sure it's in that box to the left. Okay, but anyway, there's the basics of the greatest integer function. We'll get a little more advanced in the next slide, but there we go. Okay, so now if we have to evaluate greatest integer functions, they're a little more decorative, and the reason why we have a little more decorative ones is because really the real life scenarios are very nicely modeled by this a lot of times, and unfortunately it's not usually as simple as just a single number that you're dealing with. But back to the real things are kind of modeled this way a lot. I mean, if you think about driver's licenses, okay, if you're 16, you can get a driver's license, so hey, that works, and so we have our criteria based on that. But if you're 15 years, 364 days, well, you're not old enough yet to get a driver's license. So basically the greatest integer function does that sort of thing. It takes whatever you are and only counts what you've reached, basically. So if you've reached 16, great, you're officially 16. If you haven't reached 16, no matter how close you are, you're not there yet, you're still not 16. And so this is just a mathematical way of representing that reality that exists in real life about most of the things that we do with age categories. Alright, but anyway, moving on. Alright, we've got f of 5, and we want to do f of 5 based on this function right here. Okay, well, of course, basically all we're doing is plugging in the 5 for x. So we got 2, 7 minus 5, and the greatest integer function thing, which is a little awkward to draw, but I'll do my best with that and make that a 5. And then plus 4, and it's really an order of operations thing, just work it out and kind of go from there. Okay, so I'll keep the 2, the 7 minus 5 is actually just a 2. And then the plus 4. This thing, the greatest integer of 2 is 2. So this one actually works out to be a pretty easy sort of thing. And I'll save you the drama here and just go straight to the 8 there. I'm sure nobody's shocked by that. Okay, then when we start doing the decimals and the fractions and stuff, and the positives versus negatives, here's where it starts getting a little more creative, but here it is. Okay, so now f of negative 0.1 equals exactly what we did before. Run the whole thing out, minus negative 0.1. Plus 4, but again, just kind of keep in mind that this symbol now is going to cause us to do some kind of weird things. So here we go, 7 minus that ends up being actually positive, adding I mean, so 7.1 plus 4, and again the greatest integer of 7.1 is just a clean 7, and then once you got that far, 14 plus 4 will give us an 18. Okay, so again, just be careful dealing with that, make sure you treat it differently because it is different. And so hopefully that doesn't cause too many problems there. Okay, now especially those of you who already printed out the PDF notes, you were like, oh, well, we got graphing. Even if you didn't print them out in advance, I'm sure we've been doing a lot of graphing, so it shouldn't be too much of a shock that this thing is going to show up as a graph. Alright, so let me change to nice pretty red here for this. Alright, so the greatest integer function, blah, blah, blah. Okay, so we can just go with a straight up XY chart if we want to, but honestly, unless we start throwing some decimals in here, it's not going to do very much surprising things for us, because 0 would still give us 0, and 1 would still give us 1, and 2 would give us 2. Negative 1 would still give us negative 1, and negative 2 would give us negative 2, so no big shock. So we get 0, 0, 1, 1, 2, 2, etc. And going back in the reverse. And I could take this further if I wanted to, but just for the sake of argument here, let's not. Okay, so we're looking at this, and just keep in mind, though, if I start plugging in something like 0.2, well, the greatest integer of 0.2 is 0. So now if I start plugging in decimals, and any decimal up until I reach 1, so all the way at all these other decimals, I actually still get 0 up until I hit 1. So like 0.99999 would still be 0, but then the second I actually hit 1, it jumps up. And then again, 1.1, 1.2, 1.3, all those little decimals and everything there are still going to give me a value of 1 up until I hit 2, and then it jumps up. So a lot of times this is called a step function, because basically as you go ahead and graph this, it generates what looks like a set of stairs. Okay, we've got these closed circles on the left and open circles on the right. Again, because of the way the greatest integer function works, we want whichever one is less than or equal to the thing that we're dealing with. And then again, that works in the negative direction. Now remember, if I'm at negative something, I want to go less than, so I get to negative 1. So if I get negative 0.5, I'm dropping down here to negative 1 for this. So basically that stair pattern doesn't do anything weird as we jump into the negatives, it just continues all the way through. And we get some kind of graph like this that very consistently runs the entire length, width of the graph, whatever you want to think of it as. Alright, so we got that. Technically there'd be a dot up here because it would extend it more, but I'm not going to get picky about that. If you can give me enough steps that the idea is good, then I'd be happy with that. But basically, there's your graph of the greatest integer function. Well, of course, if we can graph something, that means we can take the graph and twist it around and do various things with it. Honestly, in the assignment, they never have you do more than one alteration at a time, but I figure I'd throw 2 in one of these as an example, just to kind of kill 2 birds with one stone sort of thing. Additionally, what I'd like to talk about is on the calculator, how you do this. I'm betting on the Inspires there's probably some kind of a symbol that looks like these that you can just type in, so it won't be too much of a shock. On the folks with the 83s and 84s, it's a little bit different. You have to go find the int command, and then from there you can type in the various things that you need. Like in this case, you'd have to type in the 1/2 first, and then greatest integer, which is what the int means. I think it's under the number menu if I remember correctly. And then type in your x, and close up the parentheses, and then you hit -3. So on the TI-83, 84, that's what you're doing. On the Inspire, again, I would bet all kinds of money that you probably have a symbol similar to this that you can find. So that's how you can do these guys on the calculator. But let's make sure we can do these by hand. So here we go. Now, again, the 1/2 in front is going to be a vertical smushing. So basically all my moves are going to be just a half as high as they used to be. And then the -3 is, of course, a shift down 3. So instead of being at the origin as my first point, I'm going to shift down 3. So 1, 2, 3, and there's my first point. Okay, and he'll go across and leave a dot at the end. And then again, vertically, instead of going up by 1 between each step, I'm only going up by a half. Of course, if this was like a 3, I would jump up 3 before I made my next point, but I'm only going a half, so I'm just going to jump up a half to make my next step. And then jump up a half again, and basically just continue that the whole way. Again, I don't need you to cover the entire graph if I'm asking you to do one of these, but again, give me enough that I can tell what the heck you're talking about, and that you know what you're talking about. So there would be a pretty reasonable graph of this. And again, if you want to graph that on your calculator just to be safe, just to make sure you got it, there it is. Although the one thing the calculator won't do is it won't give you the dots and the open circles. It'll just give little segments, and it's kind of up to you to understand that you've got this sort of arrangement with the open dot on one side and the closed dot on the other. So it's one of those cases where you need to be smarter than that hunk of plastic and microchips that you're holding in your hand. Okay, moving on, we've got our reciprocal function, and reciprocal, of course, just means you flip it over, so that's all we're looking at there. So instead of f of x equals x, it's reciprocal. Alright, so one of the kind of unusual things about this is most of the graphs that we have, the kind of basic one passes through the origin in some capacity. Well, here, I can't plug in a 0. So I plug in a 0 for x, I get undefined. So that's going to cause us a problem. So we have to be a little more creative in what we do here. Well, let's start plugging in with something that's nicer. Let's plug in a 1. And if I plug in 1 for x, well, 1 over 1 is 1. So I get the 0.11. Yay, very exciting. And let's start an XY chart, because I know somebody's going to yell at me if I don't. Okay, so there's the 1, there's the 1. Alright, well if I plug in a 2, well suddenly I got 1/2. So 2 gives me 1/2. Alright, and hopefully not a big shock. As I plug in 3, I get 1/3, and notice I get smaller here. Okay, and basically, I'm not going to do this, but if we continue 4, 5, 6, 7, 8, 9, etc., I keep getting smaller and smaller fractions. So basically on one end of this thing, it's kind of coming here, and no matter what I plug in, I'm never going to quite make it a 0. It's always going to be some teeny tiny fraction, so basically what I've got here is an asymptote sort of thing going on. Okay, pretend that actually hugs the x-axis, but there you are. Okay, now I've got this kind of weird situation here between 0 and 1. I know 0 is undefined, but what if I plug in some kind of fraction? If I plug in 1/2, well, 1 over 1 over 2. And so basically I'm asking, hey, what's the reciprocal of 1/2? Well, the reciprocal of 1/2 is 2. So by going 1/2 in the x, I go 2 in the y. Okay, and I can do that similar sort of thing. Notice that this guy is just kind of reverse of it. So same basic deal. I can plug in the 1/3 and get 3. So by plugging in a smaller fraction, I get a larger result. So I have this kind of arrangement going in a vertical sort of orientation as well as the horizontal orientation here, and hopefully by no shock that we've actually got a asymptote, or an asymptote, sorry, coming this way as well. Alright, if I play this game in the negative direction, I can simply add negative signs to all these, and just for the sake of people taking notes, I don't know if you want me to do that or not, but you can imagine it, or extend the XY chart if you want. But if I put negatives on all these guys, I basically generate this same set of points down in the third quadrant, because a negative x will still give me a negative y. So basically I'll still have the -1, -1, and I'll have the 2 and the 1/2 both being negative, and then the 1/3 and the 3 both being negatives with each other. And again, I continue that other. So basically these asymptotes do carry all the way through across top to bottom and left and right for the whole graph, and then we've got this sort of arrangement here. Okay, you may recognize this as one of your conic sections, and hopefully you do. This is actually a hyperbola. Okay, but before, when you graphed them, you probably always graphed them so they open side to side or up and down. Here we're going kind of at a 45-degree diagonal, so it's a hyperbola with a 45-degree twist to it, or whatever you want to think of it as. Okay, so that's it. So very simple function gives you something that, before was this crazy equation with all kinds of squares and minuses and stuff, and it was very nasty to look at, but this is a very simple, elegant sort of equation, but it again generates that same basic thing. It's just at an angle instead of vertically or horizontally oriented. Okay, so of course, if I can graph the simple one, I should be able to graph something a little more elaborate. And so, okay, we've got, now instead of a 1 on top, I've got a -16. Okay, now typically that 16 looks like something that we multiplied by, and so we've got sort of a vertical stretching, if you will, although it's going to play out a little bit different here, and I'll show that as we go on. The negative that we're used to, being a coefficient of sorts, is going to flip it upside down, and that's still going to work. And then again, if we put a number with the x, okay, that +2, remember, if he's with the x, he's a big fat liar, and he's making us move horizontally. So basically now my graph is going to shift left 2 from where he normally would be, and that minus sign again means he's going to flip upside down. And then that 16, well, we'll talk about that as we get to it. But basically, normally the asymptotes would be right along the x and the y-axis. And again, if you think about that last graph, it didn't actually pass through the origin, so I don't have like a vertex per se to work with here that I can shift around like that. But what I can shift is the asymptotes and where they cross. So again, this guy shifts left 2, so my vertical asymptote that normally would run right along the y, he's going to run 2 to the left. So I get something roughly like that as my asymptote. I just say roughly because I'm sloppy with my handwriting. Okay, I didn't have any sort of vertical shift, which would be a number out here to the right of the expression, and there was no adding or subtracting there, so my vertical shift is a non-shift. So basically what that means is the x-axis keeps its role as an asymptote here. Alright, and then again, it's flipped, so instead of going low left and high right, I know I'm flipped upside down, so I know I'm going to be kind of low on the right side and high on the left. Okay, now as far as generating points, I don't want you to do an XY chart, but here's what I want you to do is focus on this number, this 16. Okay, well, if I think of a more stripped down one with all the other decorations, and I just think of a 16 on top and an X on the bottom, well, if I plug in a 16, I would get 1, and I'd have to go way over to the side to get a Y value of 1, so I don't want to try to have a huge graph like that. But what I could do is if I plug in a 4, notice that's the square root of 16, then I get a 4 over here, which is kind of a nice little arrangement. And basically, without a big long thing, because I'm sure you guys don't really want to hear it, basically all you need to do is figure out the square root of this number, and then from the cross of the asymptotes, you just have to go that square root over and then either up or down depending on various things like the flip or how it normally is supposed to be. So in our case here, this 16, I'm going to go from the asymptotes crossing 4 to the right, and then again, since this guy's flipped upside down, I'll go 4 down, 1, 2, 3, 4, and that gives me kind of my vertices of the hyperbola. So I do have vertices of sorts, they're just not starting at the origin like in most of the graphs that we've had. Okay, in a similar way, I know I'm going to be kind of in here in the upper left part of the graph, and the same basic idea. Start at the crossing of the asymptotes, and then take that square root and go both ways to get in the appropriate spot. So here it's left 1, 2, 3, 4, and up 1, 2, 3, 4, and we've got a nice dot there. And then from there, you should be able to draw a reasonable hyperbola through there. Just hug your asymptotes; they need love like everything else. And there you go. So there's that guy. It's maybe a little smushy, but whatever. And again, do the same thing over here. Draw it out, kind of hyperbola shaped. Hug your asymptotes, and then you got a pretty good graph there. Okay, I admit I picked a number like 16 just to kind of dramatically show the difference. Okay, if we had a 1 on top, we were really, really tight and close, and then the bigger the number we get, the further out we get with these guys. So if I put a number like 100 on top, I'd be going 10 over and 10 down before I made that dot and then tried to draw a hyperbola through there. So honestly, the smaller number you got, the probably easier it is to deal with, but again, I just wanted to show kind of an extreme example here. Okay, now piecewise functions we've dealt with before, but not too much more than evaluating. Like if I told you to do f of 13 or something like that, well, you would just check the inequalities over here, find where 13 fit in, which in this case is the bottom one, and then you plug the 13 in, crunch the numbers, and get some kind of a value. Okay, if we want a graph of this, again, that's just a visual way of showing every single possible value that goes with every single possible x that you could pick. We need to be a little more careful about how we handle it. Okay, but we just have to graph each piece in the appropriate domain that's being specified. Okay, so here I've got x squared minus 5, and I'm doing that only at x less than or equal to 1. So basically what I do is I just start graphing the thing, and then, quite honestly, graph the whole thing and then erase what you don't want, which is maybe one way you could go, but here we go. Alright, x squared minus 5, of course, is a parabola shifted down 5, and then the standard 1, 3, 5 applies, because there's no other numbers or anything like that that's twisting it around, or stretching it. So 1, 2, 3, 4, 5 gives me my vertex. Okay. And then I guess the 1, 3, 5 would go. So I would go, I'm going to do this to the left on purpose to start, because kind of that's where the inequality is sending me, less than 1. So I'll do my 1, I'll go 1, 2, 3, and I'll go up here and do 1, 2, 3, 4, 5. And again, I could probably almost fit in that 7, but again, I think this is enough points. So I have my left side of my parabola here, and of course, as sloppy as that is, here it is. Okay, and then I can take this guy to the right, so I go over 1, up 1, and make my dot. But again, I really only want to stop at that. So granted, I could keep doing dots, but I would just have to erase them anyway, so I'm going to stop there. Okay, notice I did use a solid dot here. That is important because I do have the or equal to bar. Okay, now I've got x greater than 1, so now to the right half of the graph basically, I want to do the 1/2 x plus 2. Now again, this is a little bit awkward to do, especially since my slope has a 2 on the bottom and I want to deal with a 1 as my cutoff point. So again, what I would do is go up 2, kind of start making my graph, and then go up 1 over 2, etc. Okay, and again, I know I don't need anything to the left, so I'm not going to go that way at all, but I'll do a whole lot of dots this way. And I'll draw my graph, but hopefully you're thinking right now that there is a problem, because there is. Okay, I only want to be greater than 1, and right now I'm at 0. And if you want to talk vertical line test, right now I'm failing the vertical line test because I definitely have points vertical in relation to each other, so I don't want that. So what I need to do is erase, so I'll grab my eraser here, doesn't look like fun, and I'll erase the stuff that I don't want. So I don't want anything to the left of 1. Oops, so I lost a little bit more than I wanted there, but we can work around it. We have the technology. Alright, so anyway, I want to be at 1, but not exactly, just slightly to the right of 1. So again, that's my open dot sort of scenario. So on my graph I have an open dot, and then I can now just kind of connect it. Now that open dot should be kind of at a halfway point, because if you think of a slope of up 1 over 2, each of these other grid lines are kind of at a halfway mark. So this guy should be basically at 3.5, and then just continue your line going that way. And that gives us our function, and again it's still a function because my vertical line, even though it looks like it might fail, there's not really a point there, and then I join a point there. So nowhere do I fail the vertical line test, so I still truly do have a function, and the world is still a happy place. Whew, that was close. But there's what you can do even by hand, graphing a piecewise function. Alright, now doing piecewise functions in the graphing calculator is a little more of a challenge, especially for the folks with the TI-83s and 84s. Okay, the TI Inspire, I'm betting, would have a function like this where you could write some kind of a bracket and you could type the two things in, and it spits out exactly what I did in the last screen, basically. Again, with the TI-83s and 84s, it's a little more tricky. So if you have an Inspire, you can pretty much probably ignore this whole slide. But here we go. Alright, so for 83, 84 folks, okay, basically go to your y equals screen, and for y1, what you have to do is type in this first part, but you actually have to be a little more than that. Okay, basically what you have to do to tell the calculator something weird is going on, you put it in parentheses, and then you type in your x squared minus 5, close the parentheses, and then you open a new set of parentheses and put in this guy right here, x less than or equal to 1. Okay, and then same basic thing, you have to go y2 and then put in the second piece. Alright, so then you would type in your 1 divided by 2, x, and put in your plus 2, close the parentheses, open a new set of parentheses for the inequality, x greater than 1. Okay, the inequalities are located under the test menu, which is accessed on the left side of the calculator. I'm sure you can find the button. There it is. Okay, so that's what you'd type in, and then it would actually graph the thing we had on the other screen. Just a kind of a side note, which is important in case you do have a third one, because basically if you have a third one, you might have a piece of your function that has some kind of like x plus 3, and then your criteria might not be a single one-sided inequality, it might be a compound one, so you might have something like negative 2 less than or equal to x less than or equal to 5 or something like that as the criteria, or the inequality, domain restriction, whatever you want to say. Well, to type that in, again, put in your y1 or whichever y you were on, okay, and put in the x plus 3 in parentheses, and then basically what you'd have to do is put both compound, or both parts of the compound inequality in each in separate parentheses. So you'd have to put in x greater than or equal to negative 2, make sure you read it from right to left or left to right depending on how you're going here, and then another set of parentheses with the x less than or equal to 5. So to do one compound inequality like that, just for a piecewise function, you'd have to type in 3 separate sets of parentheses. Okay, now just a little, just in case sort of thing. I know there's different versions of the software upgrades on the 83, 84, so if you have a software upgrade that allows some of these things to be avoided, then that's great, but I know on the basic operating system this is what you have. You might have an upgrade that will help let you work around that, and if you do, then great for you, but if you don't have it, there's what you have to do. Alright, now the moment you've all been waiting for, I'm sure, the word problems. Alright, now let's take, again, like I talked about with these greatest integer functions, it's really great for doing certain real-world scenario sort of things. Okay, like for instance, shipping companies like, let's say we have FedEx. It charges $8.50 to ship packages, less than 1 pound, an additional $1.50 for each additional pound, or just a portion of a pound. Okay, so the price P is given by this function here. So P of X is 8.5, so there's your $8.50 for just basically saying, hey, I'd like to mail something, and then the 1.5 per pound over that. Okay, so I kind of put the graph on here already just to kind of kill the suspense and not have it be something that you would have to draw by hand. So if you do this in your calculator, something like that is going to spit out. Again, I did this from wolframalpha.com. Again, TI Inspire folks, I bet you type in something that looks just like that. For the 83, 84 folks, you have to type into your Y1, the 8.5 plus 1.5, and then find that integer function, and then x close the parenthesis, and that's what you'd have to type in to generate this graph. Okay, but again, just like I said before, you do have to be smarter than the hunk of plastic that's talking to you here, and just keep in mind that all these little horizontal lines that will be generated by your calculator are actually horizontal lines that have a closed dot on one side and an open dot on the other. So I'm not going to do the whole thing, but just keep in mind that each of these guys looks like that little thing right there. So closed dot on the left, open dot on the right, going on for infinity. Again, I only did the first quadrant of this graph because, again, it's pretty hard to ship a negative weight object. I don't know, maybe you could try shipping helium balloons, but I don't think they'd give you credit for that. Alright, but anyway, so here's a graph that spits out your calculator. Again, I didn't have any sort of specification about how far to graph it, so I just went to 10. Of course, depending on the circumstance, you might want to go either more or less, depending on how much of the graph you cared about. But here we go. We want to determine the cost of a package that weighs 7 pounds 3 ounces. Alright, so here we go. So we're looking for 7 pounds and then just a smidge more, 3 ounces. For those of you who are unsure, 3 ounces is like 3/16 of a pound. So basically our package right here is 7 3/16. Alright, so again, 7 would be sitting right here in my graph, so I'm going to go a little higher than that so I could just use the graph itself and kind of read up here, and if I'm not reading crookedly, I think I hit about right there. So I'd have to read across to this, but of course I think an easier thing to do, since I don't have the table available to me right now, is just plug it in. So P of 7 3/16 would be 8.5 plus 1.5 times our greatest integer of 7 3/16. And of course the greatest integer of 7 3/16 is just 7. So 8.5 plus 1.5 times 7. Alright, and everybody knows that 15 times 7 is 105, so this is really 10.5. And so hopefully this plays out the way it looks on the graph. But anyway, here we go. The 8.5 and the 10.5 works out to be 19. So basically, if I want to ship something that's a little bit more than 7 pounds, it's going to cost me 19 bucks through my fictitious FedEx company. And there you go. Alright, here's our assignment, page 71, all those different things. Yeah, make sure to take heed of the note here on the bottom, no calculator until 61, but once you hit 61, it's in greatest integer problem. It's similar to the one that I just did there. It has some messy numbers, actually messier than the ones I just did. So you definitely want to use the calculator for that, even for the graphing, because I'm not going to have you graph something with really, really messy numbers by hand, so please, please, please use the calculator in that. Honestly, it's just not worth your time to make you do some messy decimal graph. When you do have that tool in your hand that can do it in just a matter of seconds instead of the several minutes it would take to do it by hand. So anyway, there it is. Good luck, and may the force be with you. And if anybody was ever wondering what happens when you just have a little bit too much free time on your hands and you play Skyrim, that's what happens.